The following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. There are two different classes that may be observing this session. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmail@ybcc.edu and I'll respond as soon as I can. All right, today we're going to go on to section 9.5. We're going to wrap up the chapter. So to the homework over the weekend is going to be section 9.5 as well as the chapter review. We will review on Monday, and then Tuesday your test is, you need to take your test by Tuesday night at 11:59 p.m. And on Tuesday there will be no class meeting. Okay, having said all that, I had a request for a problem, so we'll do that before we move on. This is from section 9.2. Excuse me, not 9.2. Yes. How about 9.3? Well, anyway, it's number 23. I'm not sure there. All right, here's the problem. We've got 81c to the fourth, all raised to the -3/2 power. Now, first of all, I want to point out that this negative sign that's outside of the parentheses is not part of the base to which the -3/2 is attached. So if I want to get rid of this negative exponent and make it positive, this is going to become negative, the quantity, 1 over 81c to the fourth, all to the +3/2 power. Okay, so now we've turned the exponent into a positive exponent. Next, I'm going to take this exponent and attach it to each piece inside. So again, I've got this negative sign outside, and then inside I've got 1 to the 3/2 power over 81 to the 3/2 power c to the fourth to the 3/2 power, okay, which is negative. And then in the numerator, let's see, 1 to the 3/2 power, 1 to the 3/2 power. Well, that would be 1 to the 1/2 power cubed. The square root of 1 is 1, 1 cubed is 1. So basically I get 1 in the numerator. Next, let's look at the 81 to the 3/2 power, okay? So 81 to the 3/2 power would be 81 to the 1/2 power cubed. The square root of 81 is 9. 9 cubed is, let's see what 9 cubed is. 9 cubed is 729. So this becomes 729. And then we're going to look at this. Power raised to a power, you'd multiply the exponents. 4 times 3/2 is 12/2 or 6. So c to the 6th power. So there's the answer. You could also write it as a -1 on top over 729 c to the 6th power. And there you have it. Okay, so now we're going to go on to section 9.5, which is solving radical equations. So let's say we've got the following equation. The square root of x minus 10 equals 1. If we square a square root, the exponent of the 2 and the index of a 2 will reduce down and in effect eliminate each other. So basically, if I square both sides of this equation, on the left side of the equation, I get x minus 10. On the right side of the equation, I get 1 squared or just 1. From there, I'm going to add 10 to both sides of the equation, and I get x equals 11. Now, when you square both sides of an equation, there is the possibility of introducing what are called extraneous solutions. These are solutions that are produced, but when you go back and check them, they don't work. So whenever we solve an equation by squaring both sides, we need to check our work. It's a good idea to check your work anytime, but especially here. Okay, so if x is 11, plugging that back into the original equation, we would get the square root of 11 minus 10 equals 1. 11 minus 10 is 1. The square root of 1 is 1, so we get 1 equals 1, so it checks. So x equals 11 is a correct solution. All right, let's take a look at another example. The square root of 5x minus 6 equals 2. One of the things that we need to do, though it's already done in these first two examples, is if we have an equation with one radical, we want to isolate that radical. It's kind of like solving absolute value equations in the last chapter, where if we had one term that was an absolute value, we wanted to separate it from everything else. Okay, so we've already got the radical term separated. So then at this point, we're going to square both sides. So on the left side, we get 5x minus 6, and on the right side, we get 2 squared, which is 4. So now going on and solving for x, we're going to add 6 to both sides of the equation. 5x equals 10. Divide both sides by 5. X equals 2. Let's check our work. Let's see. 5 times 2 minus 6. Okay. 5 times 2 is 10. 10 minus 6 is 4. The square root of 4 is 2. 2 equals 2. It checks. So our solution is correct. Now, I happen to get the same number here that I got here, but that doesn't always happen. Basically, what I'm looking for here is a true statement. A number equals itself. But in this case, the solution is 2, and it is correct. All right, let's take a look at another one. Got the square root of 1/2 x plus 3 equals 6. Again, the radical term is isolated, so we'll square both sides of the equation. On the left side, we get 1/2 x plus 3. On the right side, we get 6 squared, which is 36. Going on and isolating x eventually, we'll subtract 3 from both sides. So we get 1/2 x equals 33. Okay. Then we're going to multiply both sides by 2 to clear the fraction. So x equals 66. Let's check our work. We would have 1/2 times 66 plus 3. 1/2 times 66 is 33. 33 plus 3 is 36. The square root of 36 is 6, so 6 equals 6, and the answer checks. All right, let's take a look at another example. The square root of 3x plus 5 equals 2. I want to point out the 5 is not inside of the radical. It's a separate term. So again, the first thing we want to do is isolate the radical term. So we'll subtract 5 from both sides of the equation. We get the square root of 3x equals -3. Now that we've isolated the radical, we'll square both sides, and we get 3x equals -3, the quantity squared. -3 times -3 is +9. Then we'll divide both sides by 3, so we get x equals 3 as an answer. Checking our work, going back to the original equation and replacing x with 3, we get this. 3 times 3 is 9. The square root of 9 is 3. 8 equals 2. That's false. So this is what is known as an extraneous solution, but in fact, there is no solution. Sometimes WebAssign will ask you to find those extraneous solutions. Find the solutions, and then they'll say, does it work or is it extraneous? Looking right here where we had this, if you think about it, you could already tell there'd be no viable solution, because when you take a square root, you can't get a negative answer. So that's not going to work. But if you continue on, you come up with the potential solution, but that does not work. So there's no solution. Okay, let's see here. Let's say we've got this situation. The cube root of the quantity 12m plus 4 equals 4. Once again, we have a radical, and it has been isolated, but it's a cube root. So now we're going to cube both sides of the equation. On the left side of the equation, we'll get 12m plus 4. On the right side of the equation, 4 cubed, which is 64. Going on and solving for m, the next step, we'll subtract 4 from both sides. 12m equals 60. Then we'll divide both sides by 12. M equals 5. Let's check our work. The square root of 12 times 5 plus 4 equals 4. The cube root, that is. The cube root of 60 plus 4 equals 4. The cube root of 64 equals 4. The cube root of 64 is 4. So 4 equals 4. It checks. So our solution is correct. Okay, let's see here. Let's see here. How about this one? We have the quantity 2b plus 29 to the 1/3 power equals 3. Recall that the 1/3 power is the same as the cube root. So really, this is just a variation of this kind of problem. But again, we're going to cube both sides. So a power raised to a power, you'd multiply the exponents. 1/3 times 3 is 3/3 or 1. So basically we have 2b plus 29 equals 3 cubed, which is 27. Going on to solve for b, we'll subtract 29 from both sides of the equation. We get 2b equals -2. Divide both sides by 2, and b equals -1. Let's go back and check our potential solution. So we have the quantity 2 times -1 plus 29, all to the 1/3 power equals 3. 2 times -1 is -2. So -2 plus 29, all to the 1/3 power equals 3. -2 plus 29 is 27. 27 to the 1/3 power equals 3. The cube root, or the 1/3 power of 27, is 3. 3 equals 3, it checks, so our solution is correct. Okay, now, let's see. This says, let f of x equal the cube root of 3x minus 6 for what value or values, depending, of x is f of x equal to -3. So we're not putting -3 in the place of x, we're putting -3 in the place of f of x. So now our equation becomes -3 equals the cube root of the quantity 3x minus 6. We have an isolated radical. It's a cube root, so we'll cube both sides. -3 cubed is -27. The cube root of 3x minus 6 cubed is 3x minus 6. Going on and solving for x, we'll add 6 to both sides of the equation. -21 equals 3x. Divide both sides by 3. -7 equals x. And let's check our work. -3 equals the cube root of 3 times, well, 3 times -7. Let's write that a little better. 3 times -7 minus 6, which is -3 equals the cube root of -21 minus 6. -3 equals the cube root of -27. -3 equals, and the cube root of -27 is -3. So it checks. Our answer, x equals -7. What if we have two radicals, such as in this example? The square root of m plus 4 equals the square root of 2m minus 5. Well, again, like in the case of absolute value equations, if we have two radicals, we want to separate them, one on each side of the equation. Now, if there's two radicals and another term, things get more complicated. We're not going to go there. We're just going to limit ourselves to two radicals. So I've got one on both sides of the equation. They're both square roots, so I will square both sides, and I get m plus 4 equals 2m minus 5. I'll go ahead and solve for m on the left side of the equation. So I'm going to subtract 2m from both sides, giving me -m plus 4 equals -5. I'll subtract 4 from both sides. I get -m equals -9. Divide both sides by -1, and m equals +9. Let's plug that in and check our work. So the square root of 9 plus 4 equals the square root of 2 times 9 minus 5. The square root of 13 equals the square root of 18 minus 5. The square root of 13 equals the square root of 13. Well, off the top of my head, I don't know what the square root of 13 is, but I do know that the square root of 13 equals the square root of 13. So it checks our solution is correct. Okay, now we're going to look at some formulas where we're going to be solving for a specific variable, and it will involve roots. Let's see here. We have this formula. D equals 1.4 times the square root of h, and we're going to solve this for h. Okay. So h is locked up inside of a radical, so I need to square the radical. But the question is, do I want to divide both sides by 1.4 and then square both sides, or square both sides first? I'm going to show you that we could do it either way. So let's leave it like it is here, and let's square both sides. Again, the radical term has been isolated. The 1.4 is being multiplied by the square root of h, so it's all the same term, okay? So we're going to square this, and we're going to square that. On the left side, we get d squared. On the right side, we have a product raised to a power. So this is 1.4 squared, the square root of h squared. So d squared equals, let's see here, 1.4 squared is 1.96, and the square root of h squared is h. Then we'll divide both sides by 1.96, and we get h equals d squared over 1.96. Okay, now let's go back and let's get rid of that 1.4 before we square both sides and see what that looks like. So I've got the following. I'm going to divide both sides by 1.4. So d divided by 1.4 equals the square root of h. Then I'll come in and square both sides. I get d squared over 1.4 squared, which is 1.96, equals h. So I get the same result. But in either case, you're also going to be squaring that 1.4, sort of the coefficient there. Okay, let's take a look at this example. D equals the cube root of the quantity 12v over pi, and we are to solve for v. Let's see here, let's put little lines there. All right, I have a radical isolated that contains v, so I've got to get rid of that radical to get that v outside. So I'm going to cube both sides. So d cubed equals 12v over pi. The cube root cubed gives us the radicand inside. Solving for v, let's see, the next thing I'm going to do, I'm going to multiply by pi. So I'm going to get pi d cubed equals 12v. Then I'll divide both sides by 12, and pi equals, excuse me, v equals pi d cubed over 12. Okay, let's see here. R equals the cube root of a divided by p minus 1, and we are to solve for p. So the radical term is not isolated yet, so I'm going to add 1 to both sides of the equation and get r plus 1 equals the cube root of a over p. Then I'll come back and cube both sides, so r plus 1, the quantity cubed, equals a over p. I need to get p by itself, but p is in the denominator. So if I get rid of that a on top, I still won't have p, I'll have 1 over p. So I need to get p in the numerator. So I'm going to multiply both sides by p, which gives me p times r plus 1 cubed equals a. Now I can come back and divide both sides by r plus 1 cubed, and we get p equals a over r plus 1, the quantity cubed. And let's see here. How about this one? The cube root of x plus 4 equals -1. So we've the radical is already isolated. We didn't do it, it came that way, but we're going to cube both sides. So I get x plus 4 equals, well, -1 times -1 times -1 is -1. We'll subtract 4 from both sides. X is -5. Let's check our work. The cube root of -5 plus 4 equals -1. Cube root of -1 equals -1. Well, -1 times -1 times -1 is -1. So -1 cubed is -1. So the cube root would take you back to -1. So it checks. Let's see here. How about this one? Okay, we've got the 4th root of 21a plus 39 equals 3 times the 4th root of a minus 1. Just a little detail I want to mention. You want to make sure that you put the index there, unless it's a 2, in which case it's assumed you can leave it blank. But I've had students ace a test, except for that one little detail. It was like a cube root and they didn't put the index there or something. So make sure you put the proper index with each radical. Okay, since we're taking the 4th root, we've got 2 radical expressions. They're isolated. The 3 that's outside the radical is still part of that same term, okay? I'm going to raise both sides to the 4th power, okay? On the left side, the 4th root of 21a plus 39 raised to the 4th power is going to be 21a plus 39. But on the right side, we're going to have 3 to the 4th power and then a minus 1. Right? Because we're going to take the 4 and attach it to the 3 and attach it to the 4th root. So then I get 21a plus 39 equals 3 to the 4th is 81 times the quantity a minus 1. Distributing, 21a plus 39 equals 81a minus 81. I'm going to solve for a on the left side of the equation. So I'm going to subtract 81a from both sides, giving me what? Negative 60a plus 39 equals negative 81. Okay. Then I'm going to subtract 39 from both sides. Negative 60a equals, let's see, that's negative 120, negative 120. Divide both sides by negative 60, and a equals positive 2. Let's find out if it does. The fourth root of 21 times 2 plus 39 equals 3 times the fourth root of 2 minus 1. The fourth root of 42, is that right? Something just doesn't seem, let's see. 42 plus 39. Oh, okay, I see what's going to happen, which is going to be the fourth root of 81 equals 3 times the fourth root of 1, which is 3. Well, the fourth root of 1 is 1. The fourth root of 81 is 3. 3 equals 3. I was panicking there for a minute thinking, oh, how is that going to equal that? But it did. Okay, so a equals 2. Let's see here. One more example. We have, actually, let's do 2 more examples. Let's do this one. The square root of 3x plus 10 equals 1. So I'm going to isolate the radical by subtracting 10 from both sides of the equation. The square root of 3x equals negative 9. Square both sides. 3x equals 81. Divide by 3. X equals 27. Let's check our work. 3 times 27, the square root of that, plus 10 equals 1. The square root of 81 plus 10 equals 1. 9 plus 10 equals 1. 19 equals 1. No, it doesn't. So this would be no solution. And that would be an extraneous solution. Okay. Let's see here. Okay. Let f of x equal the fourth root of the quantity x plus 8 minus the fourth root of 2x. Then it says find all values of x for which f of x equals 0. I'm going to put a little parentheses value or values. Okay, so it's not f of 0, it's f of x equals 0. So this is going to go in the place of that, giving us the following equation. 0 equals the fourth root of the quantity x plus 8 minus the fourth root of the quantity 2x. I have 2 radicals, so I want to separate them. I'm going to add the fourth root of 2x to both sides. So now I have the fourth root of 2x equals the fourth root of x plus 8. I'm going to raise both sides to the fourth power. So 2x equals x plus 8. I'm going to go on to solve for x. I'll subtract x from both sides, and we get x equals 8. Well, let's see if that's true. So we're going to put it right in here. 0 equals the fourth root of, let's see, 8 plus 8 minus the fourth root of 2 times 8. 0 equals the fourth root of 16. The fourth root of 16 minus the fourth root of 16. 0 equals, well, wouldn't the fourth root of 16 minus the fourth root of 16 be 0? The fourth root of 16 is 2, but even before that, we can see those would cancel, so it checks. All right, so again, tonight or over the weekend, section 9.5, as well as the chapter review, so that on Monday we can review any questions you have over either section. And then Tuesday, no class meeting, just your chapter 9 test. I'll be back today at 1:15 with an office hour. If I don't see you then, have a great weekend. Let's see here. Bye now.